Good morning, everyone. This is Mike Cranky at the Cloquet Forestry Center with the Sustainable Forest Education Cooperative. And nice to have you online today. We have 12 people online representing the Forest Service, the Chippewa Superior. We have the City of Duluth Budget and Operations analysts with us today, DNR and Wildlife with the DNR Forestry. Also the Minnesota Forest Resources Council, welcome, and Consulting Foresters. So we have a great group with us. Nice to have you all online today. We've had quite interesting climate, and our speaker today is Mark Seeley, and he is a professor and extension climatologist and meteorologist with the Department of Soil, Water, and Climate at the University of Minnesota on the St. Paul campus. And he's going to talk about Minnesota historic climate change and noteworthy weather events, which I think is very appropriate considering the weather we've been having lately and also some of the programming we've been doing on climate change. So we're fortunate to have Mark with all his expertise with us today. Before I turn it over to Mark, if you would like credit today, just make sure within your registration or chat pod, let me know that you would like continuing forest education credit for the class today. This is one of 10 webinars that is being co-sponsored by the DNR Forestry. Patty Thielen is responsible for helping to co-sponsor. We appreciate that co-sponsorship. It helps us to deliver these kinds of programs to you. So that in mind, we're also going to archive Mark's webinar like we do the others. You can view the webinar again or refer it to other people. Go on to the SFEC website and then click on past webinars, and you'll be able to view Mark Seeley's webinar and also hear his presentation again today, as well as the other 20-plus webinars that we've done in the past. So with that in mind, I'd like to turn it over to Mark Seeley. Mark?
Oh, good morning, everyone, and thank you, Mike. Two quick items. I'm relatively new to the utilization of this technology. I'll do my best, and I hope my pace will be about right. I'm also aware that some of you, notably Kelly, have interests or questions regarding recent weather events and episodes in our region. And I hope that my presentation will shed some light on those, but also at the end, if there's detailed questions you want to ask, I'll try to accommodate those as well. So with that, I'll go ahead and start here. The title slide should be up, and I'll go on to the next slide, which is one I've used over the years, and it's not just mine. It represents a climate science view in general, including most of my colleagues in the north central part of the U.S., acknowledging that there are three drivers of observed climate behavior. The Earth system still responds dramatically to natural variation, and we still have all of that in play, including the geometry and fluctuations relative to the sun, periodic volcanic eruptions, and changes in polar ice and a variety of other things. We have about 4.5 billion years of evidence for that in play on the Earth climate system. We also have two human-related drivers of climate behavior, and that is transformation of the landscape, how we either occupy the landscape and change its composition, or how we exploit it and extract resources from it. And whenever we disturb the landscape, we disturb its interaction with the overlying atmosphere, and therefore we find changes in climate attributes. And then lastly, the other category, the one that's probably more commonly written about in the media these days, is the changing composition of the Earth's atmosphere, and the fact that we are contributing to changes in that composition, and it's having associated effects on certain climate parameters. So bottom line, in conjunction, all three of these categorical drivers influence the Earth's climate behavior. and that's widely acknowledged and very important to understand for context. Another important context that I want to emphasize is the one of human adaptation to climate, and that's based on our views of climate behavior. Stan Chagnon from Illinois wrote several papers on this before he retired, and I like to use his frame of reference here. The slide in front of you simply depicts four, shall we say, human perceptions of climate behavior. It's a graphical representation of these perceptions, so that, for example, on the top there with the stationary view of climate behavior, it's to say that if we measured a climate attribute like temperature or precipitation at a point on Earth for a long enough period of time, we would establish its temporal statistical properties, the long-term mean value, for example, being the central horizontal line, and then the monthly and or annual variations would be built around that central horizontal line. And then we'd have some bounds. We'd have some extreme limit on both sides, upper and lower extreme limits. So if we did that, say, for enough decades, the stationary perception of climate behavior goes like this. We would have captured everything we needed to know about climate behavior at that point on Earth, and we could utilize it. This is sometimes referred to as the Jeffersonian view of climate. Many of our founding fathers were daily climate observers and really adhered to this view of climate behavior. The second graphic below that is the cyclical perception of climate behavior. Does not have much validity in our region of the world, but has great validity in the equatorial regions of the world, where we have the classic bi-rainy climates. We have the migration of the sun greatly affects the monsoon season in some of those equatorial climates, and it behaves so cyclically that, in fact, the government weather services in those countries can use the cyclical behavior as part of their seasonal prediction tools. And so, although we don't apply it in Minnesota, it is applicable at some points on Earth. The third graphic down is the perception that has come into play in our lifetime, certainly the last several decades. It's a modification of the stationary perception that simply says if you measure climate attributes at a point on Earth for a long period of time, you can derive a central mean for those attributes, but what you find associated is a waxing and waning of the variability about that mean. So in other words, you have periods of time where the variability year to year may be somewhat compressed or not that great, as if the climate behavior is stuck in a rut or a static pattern. Or you can have also periods of time you go through where one year is distinctly different than the next. And so the year-to-year variability is more highly amplified. And that indeed is the case in Minnesota. That is especially the case in throughout our climate history. And then the last graphical perception of climate behavior is the trend shift view, which is a good fit for the climate change context. And that is that across time, we may see climate behave within certain statistical bounds at a point on Earth, and we can capture those statistical attributes over the decades. But if something changes, suddenly the climate will start to behave differently. And we have many, many examples of this over time. We have places where we've taken out forests in such a large extent that we've modified the climate. We have regions of the globe, even as we speak now, such as the Three Gorges Dam in China, where we have built a hydroelectric facility that's inundated millions and millions of acres of land and changed the local climate attributes. So there's lots of this that are in play, and in the end, what happens, of course, is with the change, then you start to get climate behavior. You start to measure attributes at the same point on Earth, but they're establishing a new population of measurements. They're different than what they were historically. And so this is called the trend shift view. I would just like to emphasize for context that we've had all of these historical perceptions of climate behavior, but fundamentally what we have in our country right now is an infrastructure that is a freshwater supply delivery system, an interstate transportation highway system, a realm of architecture, a realm of electric utility use, and a whole bunch of other things that we take for granted that is fundamentally built on a stationary perception of climate behavior. And what makes it difficult then is if we've adjusted over the settlement of this country, all our infrastructure to a stationary view, and we're now, say, in more of a trend shift perception of climate behavior, we are obviously going to need to adapt, and that's important. There are 3 reasons to accept that climate change is real. By all accounts, these are points that we highlight at most of our national meetings every year. Simply stated, the measured attributes of the Earth climate system are changing, and they're changing with statistical significance. We have 3 independently derived global data sets that we look at for that, and they all show statistical change. The statistical change, by the way, is far from uniform. It's rather dispersed, with the greater amplitude of change occurring in mid-latitude climates or polar latitude climates, and relatively little change occurring in equatorial climates. In fact, there are some equatorial climates where you can't find statistically significant climate change going on. So the climate change is there, but it's far from uniform across the Earth's surface. The second point is that our climate models now mimic our measurements of climate much better than they ever have in the past. And in fact, they fit the measured changes in climate better if we parameterize the changes on the Earth's landscape that have been induced by human civilization, and also if we characterize the changing composition of the Earth's atmosphere. And then the third reason is simply a non-climatic measurement reason. It's simply that the observed and measured physical and biological consequences in the world around us fit well with the changes in measured climate attributes, so that in effect we see changes in hydrology, we see changes in ecosystems, we see changes in the areal extent of ice, we see changes in bird migration patterns, we see changes in the whole realm of things that are going on that are a logical fit with the change in climate attributes. Across the Western Great Lakes region, the climate scientists, and I might emphasize this includes most of the Western Great Lakes states, as well as our colleagues in Canada, we're all on the same page in seeing 3 attributes that are changing. We're seeing that temperatures are changing, skewed to warmer winters and higher minimum temperatures. We're seeing that water vapor in the atmosphere around us is changing. We're seeing changes in the patterns of high dew points in our region. And lastly, we're seeing changes in the moisture attributes, both the quantity shifts in precipitation as well as a character shift in precipitation. And I'll show some examples of these. Here's the example of the statewide temperature record in Minnesota. The central horizontal line, if you will, is sort of the long-term mean value, and then this is, of course, a smooth graph incorporating about 200 climate stations, but it shows periods of relative cool, annual mean temperatures shaded in blue, and periods of relatively warm temperature patterns shaded in pink. And you can see in the most recent decades out on the far right-hand side that we have both signals of warmth emphasized with persistence, year-to-year persistence, and we also see some fairly high amplitude years in there, such as the one we're experiencing now, which, given our current pace this year, we may have the warmest year in history. If we seasonalize that, which is well worth doing to see what the seasonal disparities in the warming signal look like, we find that the winter months of December, January, and February clearly show a greater persistence and a greater amplitude of change in temperature than the months of spring or fall or summer. They nevertheless all show positive change in temperature to some degree. It's just that it's far more clear in the December in the winter season. This is true for all of the parts of our region. This is true for Ontario, Manitoba, Wisconsin, Michigan, Iowa, the Dakotas, etc. So this is a regional disparity in seasonality that's in evidence. We also see that, for example, the most 15 recent heating seasons, November through March, when we typically have to heat our buildings, we can see here pooled data from the state of Minnesota. What I'd like to point out is in the far right-hand column, this is the historical ranking back to 1895, with low-ranking numbers representing relatively warm heating seasons where we don't have to consume so much energy, and then higher numbers falling in the colder part of the distribution. And you'll see that we really only have 4 of the most recent 15 heating seasons that have arguably fallen in the cooler part of the historical distribution. All of the others have been very much in the warm part, and some extremely so, such as last year, the winter or the heating season of 2011 and 2012 was in fact the warmest in history for Minnesota. Let me go on here. The National Weather Service National Climatic Data Center released the new climate normals this last year. So our frame of reference for what we call normal or average for all the U.S. climate stations changed. This is a mandate from the World Meteorological Organization that each complete decade we revise new normals. So we migrated from using a 1971 to 2000 normals period to a 1981 to 2010 normals period. One of the interesting questions that arose from that, well, what does that do to our frame of reference? Where do we see some changes occurring? The map displayed in front of you right now is an examination of how July maximum temperatures changed as we went from the old normals to the new normals. And this analysis from the National Climatic Data Center is rather interesting in that where the green arrow is now in the central part of the country, you can see that for the most part, at many of the climate stations, the average July maximum temperature declined or diminished over what it was in the 1971 to 2000 period, whereas in the western U.S. and the eastern U.S., it mostly went upward. If we want to contrast that change in normals, we can look at January minimum then, and look what happened to January minimum temperatures. Except for a small portion of the southeastern U.S., where the green arrow is now, where it went down, every place else in the U.S., the average, what we call average January minimum temperature, went up with the new normals period. And in some cases, it went up rather magnificently, and I'll show you some examples of that. Here's Two Harbors, Minnesota, and this is trends in average winter minimum temperatures for the months of January, February, and March. And looking at the normals periods and then looking at the values derived, you will see a slow progressive migration upwards in what we use as frame of reference for average minimum temperatures. And some of these are whole degrees, I might add. So that's what Two Harbors looks like. Here's what International Falls looks like. These are, in some cases, even more dramatic. Here's what Cloquet looks like. Again, you can see how the average, what we call average minimum temperature in those months has warmed. Here's what Grand Marais looks like. And then here's what the overall normals look like. So what I've done here with Cloquet, for example, is I've dissected the month-by-month changes in the normals at Cloquet, separating the minimum temperature or overnight temperature change from the daytime or maximum temperature change. And you can see that in the minimum temperature change, the left-hand column, virtually every single month went up. The minimum temperature change was positive in all 12 months. In the middle column, the maximum temperature, it was mixed. And in fact, for some months like March, there was no change at all. And then over on the far right side is the column showing what the net result in the monthly mean was. And again, most of the monthly mean values went upward at Cloquet with the new normals. And here's a depiction of Brainerd, similarly dissecting the shifts in the overnight minimums, the daytime maximums, and then the overall mean temperature shifts. So you'll see there's not uniformity. We don't want to talk about, even within the context of the climate stations in Minnesota, we don't necessarily have uniform change, but it's pretty clear, climate station by climate station, that in fact the majority of changes have been upward in what we use as frame of reference for average temperature. As a result of this, we see some consequence in evidence. We see change in depth and duration, that soils and lakes are frozen in our region. That is to say, it's less number of days. And of course, this last spring we had record early ice out dates on many of our Minnesota lakes. And we had shallow frost penetration in the soil, as well as fewer days that our soils were frozen. In the agricultural landscape, we see more rapid breakdown of crop residues. We see later fall nitrogen applications on the soils because the soils remain warm later into the fall. We see fewer adverse weather disruptions to the outdoor construction season. We see overwinter survival rates of certain biological organisms that are larger survival rates than what we've seen in past winters. We see reduced heating degree days for our utilization of energy in the heating season or the winter season. We see larger numbers of freeze-thaw cycles, which is detrimental to, of course, our roads and highways. And many of you on the line may remember that we used to have winters where we went below the 32-degree mark and we stayed there for day after day after day, but now we witness many more freeze-thaw cycles. We see changes in animal migration, hibernation, and foraging behaviors. And in the public health arena, we see longer exposure times to molds and allergens, and we see that reflected in the patient loads of our regional care centers and our major hospitals. So this is just a sampling of the consequences that we see from those changes in measured climate attributes that I just spoke of, notably temperature change, but skewed to the winter season and skewed to the overnight minimum. We also see, as the good work at the Large Lakes Observatory at the UM Duluth campus shows, we also see that around the Great Lakes, and the graphics depicted here are from Jay Austin and Steve Coleman, who studied Lake Superior, but we simply see that the Lake Superior surface water temperature is on the rise, in fact more steeply on the rise than the air temperatures of the surrounding climate stations. And then in the bottom graphic there, we see that the overall fluctuations and extent of the ice cover on Lake Superior is in decline. So another piece of evidence that corresponds with the changes in climate attributes. And then Jim Zanlow, our former state climatologist, calculated the earlier, or the trend towards earlier dates of ice out on many of our inland lakes. And a sampling of the ice out histories from many of our inland lakes clearly shows earlier and earlier dates where the ice disappears in the late winter or the early spring. I want to move on to the water vapor attribute, which I listed earlier in the presentation, and show some examples of how it's changing. Now, this is simply a pooled graphic of summer mean temperature, June, July, August, and it shows a modest warming out here on the far right, kind of mixed signals as well, but embedded in that is disguised what the water vapor is. Here's the May through September mean temperature. So as opposed to what I showed you earlier, this is more like a air conditioning season synopsis, a synopsis of the temperature conditions during the air conditioning seasons of the last 19 years. And once again, what I'd like to show you in this case is that the lower ranking numbers means greater demand, that is a warmer air conditioning season, and you'll note that in 2011 it was the fifth ranked in terms of warmth, so lots of demand for air conditioning last year. I suspect this year may be of equal rank or maybe even higher rank the way we're tracking this year. But you'll note in the distribution in the column there, you'll note that we've had only 5 of the last 19 air conditioning seasons that have fallen in the cold part of the historical distribution. So again, we've seen a skewed nature to the demand for higher demand for air conditioning, and this is from pooled data all around the state. In these next graphics, it's the frequency of tropical-like dew points. Whenever the dew point, that is the temperature to which you'd cool the air to get condensation of its water vapor content, whenever we get to a 70-degree dew point or higher, we are experiencing a tropical-like air mass. We are experiencing an air mass more typical of 20 degrees north latitude rather than 45 degrees north latitude. And you'll see that for a couple of places, notably the Twin Cities metro area in the upper graphic and the Voyageurs National Park in the lower graphic, that the trend and the episodes of high dew points in recent years are on the rise. And we see this all over the region. We've already had some extraordinarily high dew points, in fact, in 2012. That's partly why some of our heat advisories and excessive heat warnings have been issued already this summer. As a result, what happens is there's a relationship with the overnight minimum. The summer overnight minimum temperature cannot go below the dew point. So if the dew point is on the rise, we would expect to see a slow migration upward in the overnight minimum average temperature. And indeed we do at many locations in the region. This is an example of St. Peter in south central Minnesota and the upward migration of average summertime minimum temperatures. What happens from a meteorological point of view is the water vapor content in the atmosphere as the sun goes down and the mixing depth of the atmosphere declines, the air layers stratify with less and less mixing. Volumetrically, this shrinks the volume of the atmosphere that has the water vapor and other constituents in it to a area that's closer to the surface. By the time we get into the wee hours of the night, the water vapor has set some kind of a dew point or down near the surface that the overnight minimum can't cool below, because when the air gets down that cool, the latent energy is released as the water vapor condenses to liquid water and the air temperature stabilizes right at the dew point. And so that's why we say the dew point sets a floor for the overnight minimum. As a result also of the high dew points, we've had inflated heat index values, and we've had most of our recent summers, we've had heat watches or heat advisories issued, not because the air temperature was 110 or 112 or 114 as it was back in the 1930s, but because the air temperature has been around 90 or 92 degrees, but it's been combined with a very high dew point, producing a high heat index value. Last year on July 19th, in fact, we established a new state record with 134-degree heat index at Moorhead, Minnesota. In fact, on that particular date, we were the warmest location in the northern hemisphere. because the dew point was up around 88 degrees. And so this pattern has been in evidence and been with us for most recent decades. If you look from my book, the Minnesota Weather Almanac, where I document the weather history of the state, if you look at all the historical heat waves in the state of Minnesota, what you find is that invariably almost all of the recent ones, and the reason they're highlighted in red on the listing on the slide in front of you, is they're dew point driven heat waves. They're heat waves because the dew point is so high, not because the temperature is extraordinarily high. And of course, some of these have led to not only human health problems, but some of these have led to other issues, such as a loss of poultry or loss of livestock or other things. So this is the nature of the beast, if you will, has changed. It's most of the heat waves in our region are driven by dew point now. Again, consequence of this change in the attribute of water vapor in the climate here, we see changes biologically in that certain organisms like the higher dew points and do well in them. So we see changes in population dynamics of certain pathogens, insects, and microorganisms. We see longer duration of herbicide volatility in some situations in the agricultural landscape. We see elevated water temperatures on our inland lakes and therefore more hospitable environments for algal blooms. We see increased workload on the healthcare sector because we have differentially susceptible populations to these high dew points, and we have people with certain ailments that are hypersensitive to high dew points. We see livestock stress, which I already mentioned, and we see prolific air conditioning even in the northern regions of the state that we could once count on for respite from these kinds of days. The last attribute I want to spend a little bit of time on is the moisture. The National Climatic Data Center has done trend analysis on moisture across the U.S. There are many areas, as you can see from their map, that show positive linear trends in the quantity of moisture. You'll note the Western Great Lakes in general shows rather significant positive trend in the average annual quantity of precipitation. Graphically speaking, we can look at the annual precipitation with pool data. We have over 1,500 precipitation observers in the state of Minnesota, managed by our Minnesota State Climate Office. And here's a graphic showing, again, the patterns across time from the late 19th century. And we can see the central mean value on the horizontal line, and then the relative periods of dryness highlighted in brown, and the relative periods of surplus highlighted in green. And once again, out here in the recent decades, we see a signal of persistence as well as an amplified signal in quantity. If we seasonalize that, we see that winter season has been somewhat mixed. Some above, some below, marginally so. Spring has generally been wet. The signal in spring has generally been wet. Signal in fall has generally been wet. Signal in summer has been mixed. So those are the looks at the seasonal patterns. The graphic of the pool data for year by year is depicted here, and the reason I like to show this graphic is it really shows how many or what population in the recent years has fallen above the 75th percentile, which is a fairly significant number of years that have fallen in that range. Pretty clear statistical evidence in the quantity shifts. And then, of course, we can go around the state and use some of our long-term records to look at site-by-site shifts in what we call annual normals. So once upon a time, Wilmer had an annual normal of 23 inches, and now it's over 29. We can see Brainerd was once about 23, and it's now over 28. Duluth, 29. It's now approaching 31. Cloquet, a little bit under 28 once upon a time, a little bit under 32 today. Two Harbors, 27.69, now up to 31.11. Besides the upward quantity shift in precipitation, we have seen a character shift in precipitation in that analysis shows a larger fraction of that precipitation is coming from thunderstorms. So whereas once upon a time we might have derived 60 to 65% of our annual precipitation from thunderstorms, we now have some locations and regions in the western Great Lakes that are getting fully 70 to 75% of their annual precipitation from thunderstorms. This regional analysis was done by the National Climatic Data Center some years ago and led us or motivated us to do some analysis here in Minnesota. Also, I might add the Intergovernmental Panel on Climate Change in their last assessment back in 2007. They looked at this character change in precipitation as well, and they found, as depicted in the lower map where all the blue plus signs are, they found that in all of those landscape regions, the contribution of thunderstorm rainfall to total annual precipitation was upward as well. And so, and this, by the way, excuse me. Excuse me, my throat's drying out. This, by the way, is going to be a featured chapter or section in the next IPCC report, because this is a very important change. As we look, for example, relative to what happened last month at both Duluth and Two Harbors and Cloquet and Jay Cook State Park and Moose Lake and all those places, as well as what happened at Cannon Falls earlier last month, if we look at recurrence intervals for excessive precipitation, we find that the statistical derivation of recurrence intervals is changing. Once upon a time, the hydrologic manual for the state of Minnesota would have shown a two-inch thunderstorm rain across northern Minnesota was about a once every other year proposition. That is to say, the recurrence calculation was about 1 every 2 years. If we look at the most recent 2 decades, as listed here, we find that we are getting a frequency of thunderstorm intensity of that magnitude that clearly exceeds what our historical recurrence calculation was. We're getting numbers like, well into the 20s in terms of the frequency of these 2-inch thunderstorms. And in fact, in the extreme, we're getting some rather extraordinary storms. This graphic done by our Minnesota State Climate Office illustrates geographic distribution of the 3 1,000-year storms that have occurred in south central and southeastern Minnesota since 2004. The top one was over September 14, 15, 2004. The middle one was over August, I believe it's August 18 and 19, or August 18 through 20 in 2007. And the bottom one is September 22, 23 of 2010. I don't know whether the State Climate Office will choose to put the recent Duluth storm of last month in the same category as this. I believe preliminary calculations from the climate science community is it may have been a 1 in 500 year, perhaps a 1 in 1,000 year storm, but I think they're still debating that. It's a little bit difficult, though, statistically, as climate scientists are so statistically bound to look at attributes and try to come up with statistical significance. Looking at storms of this magnitude is analogous to looking at patterns of triple plays in Major League Baseball. That is, your population of such extremes is so thin, so sparse, that it's quite difficult to come up with meaningful statistics. There is another view, and this is outside my realm of expertise, but nevertheless, I think it's interesting to look at. There are those in the earth science community that have been studying the paleoclimate records in Minnesota. And notably, they published a paper just a couple of years ago examining the stalagmite structure, the mineral structure of stalagmites in the Spring Valley caves in southeastern Minnesota, because the mineral structure that's deposited there is in direct relation to extreme flood events, extreme moisture events. Now, what they discovered is in a 3,000-year analysis of the mineral deposits, they found that the most recent decades and centuries are seeing a higher frequency of extreme flood events. So there is some paleoclimate evidence that stretches beyond what our measurement records in climate tell us. And the paleo evidence, even in a 3,000-year construct, tell us that the period we're in now is seeing a higher frequency of these extreme wet events. And one other overlooked attribute of these extreme wet events is a calendar shift. In the graphic here, which is a simple bar graph, what we've done is we've graphed the single greatest thunderstorm of each year and what month it occurs in. Once upon a time in Minnesota, this would have been May, June, or July. We would have witnessed the single greatest thunderstorm event of the year falling in the months of May, June, July. In our lifetime, however, at least over the last 3 decades, we've seen a shift later in the year. And as you'll note here, we've seen a number in June and July still, but we've also seen more in August, September, and we've even seen some extraordinary years where the single greatest episode occurred in October. So there's a subtle calendar shift in these events as well. Because thunderstorms infer so much spatial variability, and because they now dominate the character of our annual precipitation in the state more than they ever have, we have developed consequence that is about winners and losers. It's about those that get surplus and those that get deficiency. And in fact, if we document all the historic droughts in the state of Minnesota, and you have the list in front of you from my book, you will note that every year since 2005, we have had severe drought surface somewhere on the Minnesota landscape. Some area of the state has been missed consistently year after year after year since 2005. And that certainly appears to be the case again this year in 2012. We have great disparity in precipitation across the state. We have the huge disparity between those in surplus and those in deficiency. And that looks like that's going to play out again. So I'm just about wrapping up here, Mike, and maybe we can have some question time. One way this plays out, this great disparity plays out, is a singular example of that is from August of 2007. In August of 2007, in the map in front of you, we had 24 Minnesota counties designated by a red X that were declared in August 2007 to be drought disasters. They were, all symptoms of drought were in play. Declining aquifers, a shallow or little flow in the watershed, high fire danger, 30% crop loss, water restrictions for some municipalities, and a whole host of symptoms. So USDA declared those to be drought disasters eligible for federal drought assistance. In the same month of August 2007, those 7 southeastern Minnesota counties designated by a blue X were declared by FEMA to be in national flood disaster status. So they were eligible for federal flood disaster assistance. The one and only time in the history of the state of Minnesota where we have had federal disaster declarations for polar opposite reasons in play at the same time across Minnesota. And in fact, this year we could duplicate that before all is said and done. I would not be surprised if that's the case. So the implications or consequences associated with the moisture attribute change include changing our direction, our pattern, our strategies related to drainage, runoff, sediment, shoreline management, retrofits of storm sewer runoff systems, modified fisheries management on some of our watersheds, mitigation of erosion, mitigation of flooding potential, and a variety of other things. Okay, just to conclude, I wanted to make comments about a few other indicators, non-Minnesota indicators, and then that'll be the end of my remarks. This graphic shows the height of the tropopause, the northern hemisphere tropopause. This is the mixing depth of the atmosphere. This is where clouds find their home. And the height of the tropopause, the mixing depth of the atmosphere, has been increasing in recent decades. And this dovetails with the climate models as well as with our measurements. So that we see, as the atmosphere warms, we see the mixing depth gets higher and higher. In mid to high latitudes, a higher mixing depth means more powerful convection. So as we get to 45 degrees north, 50 degrees north, 55, even 60 degrees north where they've reported thunderstorms, we can get more intense convection in a deeper atmosphere. As a result, back in 2007, Manitoba, Canada reported the first ever F5 tornado in Canada's history. So there was a level of convective energy and convective storm development for the first time in Canada that could produce an F5 tornado. Similarly, up at Churchill on the Hudson Bay, which normally we don't associate intense thunderstorms with, back in 2010, they had their first ever 4-inch thunderstorm rain. They had a level of convective thunderstorm development at nearly 59 degrees north latitude that produced a 4-inch thunderstorm, something that the landscape up there is definitely not accustomed to. And lastly, the models, the community climate models that are used in the sequence of maps on this slide simply show that the 44-degree annual isotherm currently that passes through the Twin Cities area in the current climate analysis will, by the decade of 2060 to 2070, be up around International Falls. So the climate behavior that at least the temperature behavior that we ascribe to, say, the Twin Cities region of our state may have migrated to be the climate behavior of the International Falls landscape by 2070. Again, that's what the models depict. So for those who doubt or wish to dismiss evidence that climate is changing, the data clearly indicate it is happening and having consequence in Minnesota. There's no denying that. And for those that think that rabbits don't exist in the sky or pigs don't exist in the sky, I simply like to use this slide from the Cloud Appreciation Society to show that we can find such apparitions in the sky. So that's all I have, Mike. And if there's questions people want me to answer, I'll watch the chat box here and see what's up. Was the recent storm in the Ely area a derecho? I don't believe it was. I think it was just a large, complex thunderstorm that delivered downburst winds. But from a continuity standpoint and from the aerial extent of the Bow Echo, I don't think the Weather Service would classify it as a derecho. Although there were, now if this is also referring to the July 2nd storm, that was 60 to 80 mile an hour downburst winds. Those were actually measured by some of the automated systems across the northern part of the state. So those were terrible winds. But I might be wrong. The Weather Service might choose to classify that as a relatively smaller scale derecho, but I don't know. In the end, I think it'll be more of a severe thunderstorm. Trend analysis on wind events. We are in the midst of trying to pursue this. There have been some wind studies done across the region. Notably, the Large Lakes Observatory has done some for the Western Great Lakes. In fact, they've shown general increases in wind speeds for the coastal regions around Lake Superior using the Lake Superior climate stations. However, my colleagues in South Dakota and here at the University of Minnesota have found some parts of western Minnesota where the mean wind speed values have actually declined. So I'm not sure we can apply a conclusion to the region as a whole. We probably need to look at it in finer scale and see how the wind trends are changing. It's my perception that this year is one of the windiest, if not the windiest year in Minnesota history, in that the number of reported high wind speeds has been absolutely remarkable this year. The number of observers that have reported wind speeds over 40 and 50 and 60 miles an hour vastly exceeds anything in my experience, and that's about 35 years here at the University of Minnesota. So this is an important question and one that we're looking into, but I don't have anything definitive to say about it right now. Wildfire numbers and intensity. I know Lee Freilich is quite worried about this, and of course he represents a quite well-informed opinion on this. My perception with the wildfire situation is that because of the character change in precipitation and because the dominant signal is embedded in how and where thunderstorms occur, those that get left out will be prone to have a higher risk of fire. And in years where, like the Northeast was left out for a number of years, notably Cook and Lake counties, as you know, were left out in terms of adequate moisture for quite a number of years, there will be a higher risk of wildfire. Similarly, we did have wildfires associated with the agricultural landscape in southwestern Minnesota this last winter. Notably, in the late fall and early spring, we had wildfires there because the landscape, as you know, was in severe drought as a carryover from last growing season. In fact, they didn't get rescued. Many parts of southern and southwestern Minnesota did not get rescued from that drought until we had that extraordinarily wet April and May. Any other questions out there? Looks like there's 6 or 7 minutes left.
Okay, Mark, it looks like we're towards the end of the program. If anybody has any other questions, just feel free to type them into the chat pod. Otherwise, I want to say thanks for a really, really interesting program. As always, you're a real wealth of knowledge, and we're fortunate to have you in Minnesota. And for those of you that have listened to Mark on public radio, he's well known throughout Minnesota. We're fortunate to have him on our program today. So I thank you, Mark, again. And,
okay, Mike. My final word on this would be that I think adaptive management is very appropriate jargon to use here, because I think the evidence and consequence that's building up on this in our lifetime is so significant that we really do need to seriously consider adapting to these changing underlying climate patterns and also to this changing probability of extremes. I think these are all discussions worth having, and that ignoring or dismissing this, I think, is a gross mistake. And not that I'm speaking to anybody who has that attitude, but having been at this now for the better part of 4 decades, I think it really is important to discuss it and digest what is happening around us.
Very good. Mark, thank you again. I know you're in high demand, so to take the time away from your busy schedule to present today, I really do appreciate it. And to our audience, just talking with Tony D'Amato, and we're going to have another adaptive management and climate change workshop coming up this winter for forest managers and natural resource land managers. So we're working on that program again that can help land managers to make good decisions based upon the probability of the climate change that Mark is talking about. So just a couple announcements. Our next webinar is August 14th, Forest Management Guidelines Revisions with Robert Slezak, Site Level Program Coordinator with the Minnesota Forest Resource Council. And we have four programs coming up this fall. August 22nd, Forest Products Utilization Marketing Workshop. We're going to have a tour of the mill, the Sappi Mill here in Cloquet, and also Jim Parma will be discussing from Bell Pole the pole market. On August 23rd, Tom Burke, professor at the University of Minnesota, will be helping with designing a timber sale, timber cruising field day at the Cloquet Forestry Center. And then I'm working on a new program that's almost finalized, September 25th, Forest Roads Wetland Crossing Workshop. Rick Dahlman, Dick Rossman, and others will be helping us, Charlie Blinn. And beginning October 1, we have a Natural Models for Ecological Forestry Minnesota applications with Brian Palick, Dr. Jerry Franklin from the University of Washington, Dr. David Mladenoff from University of Wisconsin, and others. This will be the kickoff for the SFEC Ecological Classification Silviculture class series. So if any of you are interested in that series, I'll be getting out an announcement again soon. So with that in mind, I hope you have a really good rest of the summer. I hope the weather moderates a little bit and things cool off a little bit. But thanks again, Mark, for your fine presentation, and looking forward to our next webinar coming up on August 14th. So bye for now.
Okay, thank you very much.
Okay, thank you.